Hi students. So today I'm going to start the lecture on 3D stress and strain. In the previous class I discussed some aspects about stress and strain, and also we discussed about different structural members. Now we are going to go deeply into the 3D situation because this is something which is very important as far as aerospace structures are concerned. It will also let you understand different aspects about composite materials and later on about the key failure theories which are applied in any structural system. So this is lecture 68 in our course and I am Dr. Ranjan Ganguly. Now let us start with the simple problem we use to introduce the concept of stress and strain. If we take a rod, let's say the rod has a length L and we subject it to a force F, then what happens is that the rod extends by a small amount, that is delta L. So in this system what we can do is we can define two parameters. These are stress and strain. So stress is defined as the force divided by the area of the cross section. So in this case, if we say that this is a circle, then pi r square will be the area A here. And also strain is defined as delta L by L. So it is the extension divided by the original length. So these are some fundamental measures, and you can very easily see in the case of a simple specimen like this, you can apply a force in one direction. This is a uniaxial force, and you can simply measure the strain and you can also find the stress. So that's the basic thing about stress and strain in 1D or one dimension. Now we can think of this concept in terms of multi-dimension or typically three dimension as the case is in the real world. So let's say we have an aircraft. Now what happens is that different points on the aircraft have different levels of stress associated with them. So let's say we take a particular point which I have shown in red here, and what will happen is that associated with this point there is going to be a stress tensor. Now, this stress tensor, we can also think of it as a matrix, is given by this matrix here. You can see that there are these three normal stresses, sigma xx, sigma yy, sigma zz or sigma zz. And then there are these tau components which are shear stresses. So these are xy, xz and yz. So what happens is that you are going to get in general 9 such components here, and therefore we can say that stress is going to be a matrix at a given point, and different points on this aircraft are going to be subject to different stress tensors or matrices. Now we are going to look at the physical fact about what are these different stress components. So let's start with some simple cases and build up this particular stress matrix here. So here I have shown a typical cube here, and in this cube we have the stresses which act on the different faces. So let's say this face is here and this face is here. These are both corresponding to the x is constant plane. That means in this particular face x is constant and so is the x value here. These are x is constant plane. So why that helps you is that you can essentially get the shear stresses using that particular thinking. So of course we are going to have the normal stress, the sigma xx points in the x direction, and then on this back side there is a sigma xx to balance this force. Now if we look at the shear stresses here, there is going to be a tau xc and a tau xy. So these are both in the x plane, so you have the x in front, and then the direction is the y direction and the z direction. So that's how you get this particular directionality of the shear stresses. Now this is the one which you get in the positive or the direction which is facing towards you or the outside. Now on the back side what you do is you flip the direction of the shear stresses because that's required to essentially balance them out. So if we have a stress in this direction, we have a stress in this direction, and this keeps the body in equilibrium. So this is the stresses we got on the x is equal to constant plane, and next we are going to look at the y equals to constant plane. So that corresponds to these two faces of this cube here. Now again you have the normal stresses here, the sigma yy's, they are acting out of this face. And then if we look at this face here, for example, which is on the positive side, we get very clearly two components. So they are going to be tau yx and tau yz. Now again, this is in the y equals constant plane. This is pointing to the x direction. This is pointing to the z direction. And on the reverse side, you have the shear stresses flipped in the reverse direction again to maintain the equilibrium condition here. So now we look at the third case, which is the z equals constant plane. Now here we have this face here and we have the back face there. Now what happens here again is that we have the sigma zz, which is going outward of this face, and these are the normal stresses. Also we have the tau zy and the tau zx. The tau zx will go toward the x direction, the tau zy is going toward the y direction, and the z represents that you are in the z is constant plane. Similarly, on that side here, the back side here, you will have the two shear forces, and these are essentially acting in the reverse direction, the shear stresses. So that gives us the idea about these 6 components, or rather I should say the 9 components of the stress matrix or tensor. Now here I finally put all these together. Now in many books you see this all together and that comes out as a very crowded figure. But what I have done here is on the figure I have shown in red the stresses which act on the directions of the cube which are facing outward. And then in the blue I have given the directions of the stresses on the sides of the cube which are facing in the back direction or in the down direction. So you can now clearly see that there are going to be 3 normal stresses, sigma xx, sigma yy and sigma zz, and there are going to be a total of 1, 2, 3, 4, 5, 6 shear stresses. So for example, you have a stress such as tau xc, here you have tau xc here, but you will also encounter stresses such as tau zx here and so on. So there are going to be these kind of stresses which are present here. Now, fortunately, one of the things which happens is that this stress matrix or tensor simplifies, and that happens because this cube is in an equilibrium condition, and therefore, if we were to take moments about a particular point, we are going to find that these shear stresses end up being symmetric. So these equilibrium equations are given by these 6 equations here. Of course, we have already enforced fx, fy and fz to be 0 because we selected the directions in that manner. So for example, sigma xx is matched out by sigma xx here, tau yx is matched out by tau yx here, and so on. But for the moments to actually come to 0, what needs to happen is that symmetry of this sigma matrix is required. So symmetry of that matrix means that the shear stresses are symmetric, which means that tau yx is tau xy, tau yz is tau zy, and tau zx is tau xc. Now this gives us a lot of simplicity because instead of writing sigma as a matrix, I can now write sigma as a vector. And in many books you will see that sigma is actually written out as a vector. So you will have 3 normal stresses, sigma xx, sigma yy, sigma zz, or sigma zz, and then you will have tau xz, tau x, tau yz, tau xz, and tau xy. So these are the 3 shear stresses present here. So this stress state, if you know it, you essentially know the stress at a given point on that particular material. So the word stress state is sometimes used to define this particular quantity. It implicitly means that you are talking about all 6 components of the stress at any given point. If you know it, you are very well satisfied as a structural engineer. So now let's again get back to our aircraft structure. So what we can now see that at any given point on this aircraft, there is going to be a stress tensor, or we can now say from our knowledge about the symmetry of the shear stresses that this can be written as a stress vector. So this is going to make our life somewhat simpler in terms of notation and so on. So it's a very important fact to remember that stress is also a point property, and at any given point on a structure or a solid system, you have a stress vector there. Now, of course, if we recall our problem here, which we started with the unidirectional problem or the one-dimensional problem, we saw that there was a stress, but there was also a strain. So whenever we apply a stress, for example, here in this direction, what we get is a strain in this direction. So for our current problem, this would be sigma xx, and so this would lead us to a strain which would be epsilon xx here. Now there would be also deformations in the different axes. So there would be a deformation in this direction and in this direction. So these lateral deformations are also going to lead us to the different parts of the strain and stress vector here. So what we can also now say is that for any given point on the aircraft, there is going to be a strain vector, and the strain vector is again given in a manner very similar to the stress vector. Now you have three normal components. These are epsilon xx, epsilon yy, and epsilon zz. And you have three shear strain components. These are given by gamma yz, gamma xz, and gamma xy. So just to recapitulate and sink it firmly in your mind, it's very clear that for any given point on the aircraft, you are going to have a strain vector and you are going to have a stress vector, and the dimensions of these vectors are 6 by 1. So there are essentially 6 strains and there are 6 stresses. So always remember there are 3 normal stresses, 3 shear stresses. Normal stresses are represented by sigma here, shear stresses by tau, and there are 3 normal strains represented by epsilon and 3 shear strains represented by gamma. Now just like we saw for the 1D case that the stress and strain are related because there is a material there. Now the stress and strain are of course purely quantities coming from geometry and forcing, but what happens is that when the material enters into the picture you get this value E. So sigma is E epsilon, that's the Hooke's law. That is something which is very important, and it's important to remember that E is the Young's modulus and is a material property, and it comes to us from experiment. So again remember that we are only talking about the elastic or linear region of this curve, and that is why we can write this very simple linear relation: sigma is E into epsilon. So we are subjecting the material only to small levels of stresses and strains, so that's letting us stay in this linear region. So now what we can immediately realize that there will be some relationship between this epsilon, which is the stress or rather the strain vector, and sigma, which is the stress vector, and this relationship has this form: epsilon is A into sigma. Now A here is known as the compliance matrix, and generally this matrix is easier to obtain from experiment. So what we can do is we can subject the material to different stresses. We can put one stress here, all the remaining 0, and then we can measure the strains and so on. So there are ways to get this kind of matrix from various experiments. Now correspondingly, there is one more relationship, that is sigma is C into epsilon, where the matrix C contains what are known as the elastic constants. So remember that A contains compliance and C contains the elastic constants. And of course, you can clearly see the relationship will be there between these two matrices, that C is the inverse of A. So essentially, if we have calculated the A matrix somehow, we have obtained it from experiments, then we can very easily get the C matrix. So that's typically what is done in practice. So now one more thing which happens is that these matrices end up being symmetric and positive definite, and that happens because there's a certain physical fact at work here, which is that the strain energy density, which is given by W, can be represented as half sigma T A sigma is greater than 0, or half epsilon T C into epsilon is greater than 0. So what this means is that these are quadratic forms which are positive, and therefore the matrix A and C are symmetric and positive definite. Therefore this also would mean that they have positive eigenvalues and so on, which we are going to consider later, but right now just think of it as being a symmetric positive definite matrix. If you are not familiar with that, at the end of the video in the end screen I'm going to leave you a lecture which I made in my optimization course, where I talk about positive definite quadratic forms and the symmetric matrices which come out of there. So there are two equations to remember: epsilon is A sigma and sigma is C epsilon. So the fact is that these are matrices which are size 6 by 6. So essentially you have 6 stresses being related to 6 strains. So now I have put it out here, and you can of course clearly see that I am going to have this full matrix here. Now fortunately we will see that this matrix is symmetric, and therefore there are only going to be 21 elastic constants and 21 elastic appliances which are independent. Now to see that very carefully, I have given out this matrix in full here. I have not given this half because do remember this is a symmetric matrix. So 2 1 equals 1 2 and so on. That is A12 is equal to A21. But let's count it now. 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21. So we have 21 possible elastic constants and compliances in a typical linearly elastic material, and this kind of material is known as an anisotropic material. It is the most general material, and therefore that's the material which will be something which we can start from. Now there are many simple materials which we are going to consider later. So the most important ones being the orthotropic materials, which are typical of composite structures, and the other one are the isotropic materials, which are most typical of metals. So these are the ones which we are going to consider in our next lecture. Now in today's lecture, the main thing to remember is that at any given point on an aircraft, there is a stress vector, there is a strain vector, and these are related by a compliance matrix which is symmetric and positive definite. So now we know the stress state and the strain state. If we can calculate that, there are many things we can do. Why we go through all this math is that essentially we need to design the aircraft such that it does not fail. So remember, failure can take place in any point, and therefore we need to find at every point whether a certain failure criteria is satisfied or not. So what is going to happen is that these stresses or strains are going to lead us to this particular failure theory, because what happens, the failure theory uses certain concepts like principal stresses, maximum shear stress, and so on, and those all come from knowledge of the stress matrix or the stress vector. So once you know the stress state, you can very easily calculate the principal stresses, and then you can work with failure criteria such as the Tresca failure criteria, the von Mises failure criteria, and so on. So today you clearly saw that stress is more complex than one thinks in typical first level courses such as mechanics of material, and it's actually not very complex to think of it, but the way things are taught is that it's taught in the way it developed in the past. So people were always fond of scalars and so on, but you can always think of this as a vector, and you can think in terms of vectors and matrices because that is more amenable to the various computerized solutions which you have nowadays. So I'll end this lecture today, and in the next lecture I'm going to take the last matrix which we looked at, which had 21 coefficients, and I'm going to see how that matrix essentially becomes simpler for orthotropic materials and becomes really simple when you have isotropic materials, because in isotropic materials you have only two material properties, and they are going to be the Young's modulus E and the Poisson ratio nu. So I'll end my video now, and I will see you in a lecture sometime soon. See you then.